Hey, welcome. So, if you've ever dipped your toes into machine learning, you definitely know the feeling. You're all set to solve a problem and bam, you're hit with this massive, seemingly endless list of algorithms. It can be a lot. Today, we're going to cut right through all that noise and build a super clear, practical guide for picking the perfect model for your project.
You've probably seen this question everywhere. It's one of the most common things you'll find on sites like Stack Overflow or Reddit. And hey, if you've asked this yourself, trust me, you are in very good company. It's the classic hurdle for so many people starting out. And the answer? Well, it's not always so simple.
And this is exactly why it's so confusing, right? I like to call it the algorithm overload. It feels like you have to be a walking encyclopedia of all these models just to get your foot in the door. But don't worry. The whole point of this explainer is to bring some serious order to this chaos and give you a solid framework to navigate this sea of options.
To do that, we're going to use what I call the funnel of clarity. It's simple. We'll start with that feeling of overload, then we'll start filtering, first by our goal, then by our data. After that, we'll get into the core theory behind it all, the bias-variance trade-off, and finally, we'll reveal what the pros actually do out there in the real world. All right, let's dive in.
So, we've all been there, staring at that wall of algorithms, feeling totally overwhelmed. The very first step toward clarity isn't memorizing every single one. Nope. It's about adopting a certain mindset. You see, experts follow two basic, foundational rules that simplify the entire process right from the get-go.
These two rules, coming straight from seasoned pros, are your guiding star. First off, if you don't really get how a model works under the hood, you can't tweak it, you can't optimize it, and you won't even know if its answers make any sense. Seriously, it's way better to do great work with a simple model than sloppy work with a fancy, complex one. And that brings us to rule number 2, start simple. A basic logistic regression is super fast to train and easy to understand. Don't jump straight to a massive neural network when a simpler model might do the job just fine.
Okay, with those rules in our back pocket, let's apply our first and, honestly, most important filter, your goal. What is it you're actually trying to do? To help us out, we're going to borrow the brilliant logic from the famous scikit-learn algorithm cheat sheet. It all kicks off with one really simple question.
So, first things first, look at what you want to predict. Are you trying to put something into a distinct bucket? Like, is this email spam or not spam? Is this customer going to stick around or are they going to leave? Is this a picture of a cat, a dog, or a bird?
If the answer is yes, then hey, congratulations. You've just wiped out a massive chunk of that algorithm cloud. You are officially in the world of classification. Your list of candidates now includes models like logistic regression, a great, powerful starting point, or maybe something like decision trees, which basically work by asking a bunch of if-then questions.
But what if you're not predicting a category? What if you're trying to predict a number, a continuous value? For instance, what's the future price of this house going to be? Or how many widgets are we going to sell next quarter?
If that's your goal, then you need a regression model. Simple as that. This narrows your choices down to algorithms like linear regression, ridge regression, or maybe support vector regression. Just by defining your goal as either classification or regression, we've already cut our problem in half. See? Much more manageable.
Okay, so we've picked our path, classification or regression. Now it's time to apply our second filter, the data itself. The practical reality of your dataset puts some real constraints on which models are even possible to use.
Now here's a key rule of thumb that a lot of data scientists use, the 100,000 sample threshold. The size of your dataset is a major fork in the road. Why? Because the way algorithms behave and how efficient they are changes a lot as you scale things up.
And what's really interesting here is the why behind this split. For smaller datasets, under 100K samples, classic algorithms like K-nearest neighbors are fantastic. But KNN works by comparing a new data point to every single other point in your training data. Imagine doing that with millions of records. It would be incredibly slow. That's why for larger datasets, you need models that learn incrementally. This is where gradient descent methods shine, things like SGD classifiers and, of course, neural networks. They learn from small batches of data at a time, which makes them way more efficient at scale.
The other huge piece of the puzzle is your data structure. Is it structured or unstructured? Structured data is the nice, neat stuff you'd find in a spreadsheet, rows and columns all organized. Most of the classic machine learning models are built for this. Unstructured data is, well, it's everything else. Images, raw text from a book, audio files. For this kind of data, especially when you have a lot of it, Neural networks are often the undisputed champs.
So our funnel has now given us a pretty solid short list of models to try. Now it's time to understand the big idea that explains why some models work better than others in different situations. And that idea is the bias-variance trade-off.
This concept is a classic. It describes this fundamental balancing act that every single data scientist has to deal with. See, you want a model that's accurate, obviously, but you also need it to generalize well to new data it's never seen before. The trade-off is that it's almost impossible to get a perfect score on both of those things at the same time. This illustrates the trade-off perfectly. Think of it like you're at a shooting range. Bias is the error you get from having the wrong assumptions. A high-bias model is too simple. Its shots are all clumped tightly together, but they're all way off the bullseye. That's called underfitting. Variance, on the other hand, is error from being too sensitive. A high-variance model is too complex. It basically memorizes the noise in your training data. So when you show it new data, its shots are scattered all over the place. That's overfitting. The real goal is to find that sweet spot, low bias and low variance, right in the center of the target. Okay, we've walked through the theory, the rules of thumb, and the filters. We've built our funnel of clarity. But now it's time to pull back the curtain and talk about the single most important part of this whole process, what professionals actually do when all the theory meets the real world.
This quote really says it all. The funnel framework we just built, it's fantastic for getting you a strong shortlist of candidate models. It helps you avoid wasting precious time on algorithms that are just a terrible fit. But once you have that shortlist, there is absolutely no substitute for just testing them. You have to run the race. You train each model and you evaluate its performance on data it hasn't seen before. The numbers do not lie.
Here's a great way to think about it. Imagine you're at a restaurant. You could sit there and agonize forever about whether to order the chicken or the fish. But at the end of the day, a fantastic meal depends more on the quality of the ingredients and the skill of the chef than the specific dish you ordered. In data science, your data is the ingredients, and how you clean and prepare it, that's the chef's skill. The model you pick is just one part of the recipe. So let's put it all together into a clear workflow. Number 1, use the funnel, your goal, and your data to create a smart shortlist of models. Number 2, always start by building the simplest one on your list. Number 3, test them all. Let the performance numbers guide your final decision. And maybe most importantly, number 4, remember that your biggest performance boost will almost always come from improving your data, not from hunting for some magical, obscure algorithm. And that leaves us with one last thing to think about. We started this whole journey by asking how to choose the best model. But after everything we've talked about, maybe the more important question is this one. Is the real goal to find the best model, or is it to build the best data? Something to chew on for your next project. Thanks for watching.